Hi everyone, this is Mr. Cervone. Welcome to my math channel. In today's Do Now, we have the following two problems. Number one, in a right triangle, an altitude that is drawn to the hypotenuse of a triangle divides the hypotenuse into two segments of length 2 and 8. What is the length of this altitude? Okay, so for number one, we have the following scenario. As you can see in the figure, the hypotenuse is being divided into 2 and 8 by the altitude of the right triangle. Our goal is to find h, the altitude. As you can remember, h can be expressed as the geometric mean between 2 and 8, or in more general form, the altitude is the geometric mean between the left piece and the right piece of the hypotenuse. So let's do the math here. Also, let's set up the proportion. So h is the mean proportional, or the geometric mean, between 2 and 8, okay? So after we cross multiply, we end up with h squared is equal to 16. Therefore, h has to be equal to, in this case, we're going to take only the principal root, so it's only going to be positive 4, because you can only have a positive figure in a geometric figure. Okay, so the answer is 4. Now for the second question, we want to graph these two equations here. So here we have our TI-84 plus. Obviously, you can use also the TI-83. So let's input the equation. So the first equation is half x. So we write in parentheses 1/2, close parentheses, then write x plus 1. Enter. Now for the second equation, we write negative x plus 4. Okay, and then press enter. Okay, once we're done, we can now press the button graph and graph these two equations, okay? All right, so let's say you want to view the intersection better here. You can, for example, go to zoom, for example, and pick different types of zooming modes here. For example, let's say you want to zoom fit, or I believe it should have a zoom square somewhere. Let's see if I can find it. Okay, there you go. Zoom square is number 5. Okay, so you can actually see it better. Basically, what a zoom square does, it gives the same number of units on the x and the y axis on the screen itself, okay? Okay, then you have another function, for example, zoom fit, okay? So it fits it in a proper way so you can see it better. So let's try that one out, see what happens in this case. Okay, either way, you can see that these two graphs intersect. But the question is, how do these two graphs compare and differ? Okay, so let's look at a better graph that I have prepared for you guys using Geometry Sketchpad, where the units on the x and y are not stretched, but they are the same in both directions. Here's the graph of half x plus 1 and negative 2x plus 4, okay? So what can you say about this graph? How do they compare, or how do they differ? Well, maybe we can say they both compare in a way. Maybe they're intersect the first quadrant, but there's really not much to say about comparisons. But we can say something here. They're different. In what sense? It seems like that these two graphs here, that these two equations are perpendicular to each other, okay? And as a matter of fact, in today's lesson, that's what we're going to look at. Perpendicular slopes, okay? So let's first define perpendicular slopes, okay? So here we have, for example, one of the equation is half x, okay? So let me write this here, 1/2. The slope here, let me call it equation number 1, has a slope of 1/2 x. Now, the second slope, or the slope of the second equation here, is equal to negative 2. So how do these two slopes compare? It turns out that they're actually the negative reciprocal. And that is really the definition of the slope, which is also a theorem. So let me introduce it to you. The theorem states two lines are perpendicular if and only if the product of their slopes is 1, which is also the negative reciprocal of each other, okay? Why is it an if and only if statement? Because remember, it's a biconditional statement. P if and only if Q, which means that if P then Q has to be true, and also if Q then P has to be true as well. If you don't know what I'm talking about, you can go back to the logic unit and review this. That means that it goes in both directions, meaning that, okay, if two lines are perpendicular, then the product of their slopes is -1. And if the product of their slope is -1, then the lines are also perpendicular. So let's say we want to prove this theorem. In order to prove it, we will have to prove both. First, the conditional statement, and secondly, the converse of the statement, this one, okay? Let's do the first one only in today's lesson. You can actually, if you're interested, you can look at the converse of the statement. You can prove it as well. Okay, so let's do the first one. Let's say we want to prove this statement, if P then Q. If two lines are perpendicular, then the product of their slopes is -1, okay? So let's think about what is given in this case. Well, the given is always the hypothesis, okay? So let's write given. In this case, the lines are perpendicular. So L perpendicular to K, or line L perpendicular to line K. And we want to prove the following, that the product of the slopes is -1. Okay, so let me call it M sub L times M sub K equal to -1. Let's look at the first given. So here we have the following. Let me write this down. Given that line L is perpendicular to line K, what can you say here? Well, we can say that this angle is a right angle, okay? Given that L is perpendicular to K, comma, we're going to call it angle XZ, Y is a right angle, okay? Now, why is it a right angle? Because we know that because of the definition of perpendicular lines, okay? Now, if you look at this problem here, how is this problem similar to what we did in the do now? If we scroll back here to the do now for number 1, we had a right triangle in the hypotenuse here, okay? So we can somehow use that because here we also have a right triangle, namely triangle XZY and its altitude ZW, okay? So let's see how we can use that. But first, let's establish the slopes here, okay? Now, the slope of line L, what is that equal to in terms of X, Y, Z, and W? Okay, so this is line L. So the slope is the rise, which is this one. So let me highlight this over this one, okay? So we have these two here. Okay, so here we're gonna write that the rise is WZ over, and the run is WX, okay? And similarly, the slope of line K is equal to, in this case, let me raise the yellow highlight here. Now let me draw in the new one. So we have this rise, and as a matter of fact, it goes down here, right? And then it goes to the right. So that is going to be negative. So it's going to be negative WZ over WY, okay? So how can we use this information now? Well, what we can do here is apply the geometric mean for right triangle, because we know that this angle over here is a right angle, okay? Namely angle XZW. Okay, so in this case, we can say that WZ, which is the altitude, is the geometric mean between XW or WX and WY, okay? as you remember, we actually did something similar like this in the do now, where we said that the altitude is the geometric mean between the left piece and the right piece of the hypotenuse, okay? Okay, so now, how do we use this information? Well, the first thing we want to do is to look at these slopes, okay? And multiply them with each other and see what we get. If we end up with -1, then we're actually done, okay? So let's multiply these. So if we take the slope of L times the slope of line K, we obtain the following here, okay? Let me actually draw an arrow because it's a little bit more accurate by doing an arrow. So we have WZ over WX by substitution times, and then we have in parentheses, negative WZ over WY, okay? Okay, there's really nothing much we can say yet, but there's something that we can do here now with the geometric mean that we just developed, okay? So notice here how we have WZ over WX, and here we have WZ over WX, right? So what can we do here? We can actually substitute this ratio for WZ over WX, right? Because they're equal. So let me write this here, that by substitution, we can say that WY over, let me write it better, WY over WZ times negative WZ over WY has to be true, right? By substitution. And that is equal to, let me write equal to the slope of L times the slope of K, all right? So there's something we can do here. Notice that, let me use a different color. Notice that here we have WY and WY in the numerator and denominator, okay? And also, I'm going to use another color here. Let me use, I don't know, this one. This one is equal to this one, okay? You can actually rewrite it a little different to see what I'm trying to say here. WY, I can actually push the WY on the other side, times, and then we have negative WZ over WZ here. And that is equal to the product of the slopes. I mean, you can see right away that WY over WY is just 1. And then we have WZ over WZ is also 1, right? So, and that is again the product of the slopes. So that means that here we can clearly see that the slope of line L times the slope of line K is just equal to -1. And that is actually it. We just proved it, okay? So that actually now proves the conditional statement, this one we just did, okay? Now, if you want to prove the converse of the conditional statement, you would actually have to work the other way around and assume that this is true, okay? And then somehow go back to this step, and then from this step go back over here, and so on and so on. And then at the end, you would prove that you end up with L is perpendicular to K, okay? So that's how you can prove it. But anyways, it is a theorem, it is a biconditional theorem, and it's always valid, okay? Now, how do we use this theorem in geometry? So let me show you an example. Let's say you have the following problem here. Find the equation of a line through point 4, 1 perpendicular to the line 2x equal to -3y plus 7. Okay. So the fact that it says perpendicular means that the slope is the negative reciprocal of the slope of this line here. However, this line is not in slope-intercept form, and we cannot see what the slope is. So let's change this first into slope-intercept form, okay? So again, you have 2x equal to -3y plus 7. Okay, so let's first, what we can do, we can actually subtract 7 on both sides, okay? So you end up with 2x minus 7 is equal to negative 3y. You can actually rewrite it the other way and say that negative 3y is equal to 2x minus 7, okay? All right, so now we can divide both sides by negative 3 to obtain the following. Y is equal to negative 2/3 x plus 7/3. Okay, now we want to find another equation that is perpendicular. So let me call it y2. Okay, that's the second one, the second equation that is perpendicular to it. That is going to have a slope of what? Of 3/2. Okay, because now we want to make sure that the product of the slopes is negative 1. So we're going to write 3/2 x and then plus b. How do we find the y-intercept b? Now we have a point here, 4, 1. So we say that 1 is equal to 3/2 times 4 and then plus b. That means that 1 is equal to 6 plus b. Therefore, b has to be negative 5, okay? So the final equation here, the one that is perpendicular to the original equation given, through point 4, 1, is going to be 3/2 x and then minus 5, okay? And that is the answer. How would you double check that this is indeed correct or that these two are perpendicular? Okay, first of all, we can multiply the slopes and the product's negative 1. We can also graph it just to have an idea on how it looks like, okay? So first you input the equations here, as you can see, and then you hit graph. So that's the first equation, negative 2/3 x plus 7/3. And here's the second one with 3/2 x minus 5, okay? You can also zoom it in a different way if you would like to. For example, let's do zoom square. I know it's kind of hard to see it on the calculator if these are indeed perpendicular or not, but we have a clear idea if they are, okay? There you go. They actually do look perpendicular, so yeah, they are perpendicular, okay? Let's look at another problem that is kind of similar. Find the equation of the line that passes through point negative 2, negative 1, perpendicular to the line 3x minus 4y equal to 21. Again, we want to change this equation to slope-intercept form so we can see the slope. All right, so let me rewrite it. 3x minus 4y equals to 21. Again, let's subtract 3x. So we end up with negative 4y equal to negative 3x plus 21. And then divide everything by negative 4. So here we have 3/4 x. Okay, and then we have negative 21 over 4. Okay, so it's actually better to work with fractions rather than decimals because it's more tedious to find the reciprocal or the negative reciprocal of a decimal. Plus, you might end up with numbers that you might have to round. So it's better to deal or to work with fractions in this case, okay? All right, so again, the second equation is going to have a negative reciprocal slope, which is a negative 4/3 x, and then again, plus b. Let me write the b a little better. And then we input this point here. So negative 1 is equal to negative 4/3 times negative 2, and then plus b, okay? So now we're going to multiply this out. So we're going to end up with 8/3 and then plus b. So let's convert the negative 1 to thirds. So there will be negative 3/3 equals to 8/3 plus b. That means that the b value is going to be negative 3/3 minus 8/3, okay? So what do we get here? So we get a b value which is equal to negative 11/3, okay? So that means that the equation of the line perpendicular to the original equation given is equal to negative 4/3 x and then minus 11/3, okay? It's always a good idea to also think, okay, does that make sense? It does, right? Because one of them has a very, like for example, this one, the y-intercept is very low. This one is a little higher for the new equation. Again, it's a good idea to always graph these. So let's get our calculator and graph it. So when you graph it, you input this, then you hit graph, and let's see what happens. That's the first equation, the second equation, and yes, they're perpendicular. So let me see something if they intercept, where they intercept, because it's very close to the y-axis here. So we can do is zoom in, okay? And we can now select where we want to zoom in. For example, we want to zoom in near the point of intersection here, just to make sure. Okay, yeah, you can definitely see that the first equation, this one, intercepts at -21/4, all right? And the other one intercepts a little higher, -11/3, okay? Yeah, and they're definitely perpendicular here, you can see. And yeah, so that's it. That's the answer for the second problem. But anyways, that is really the lesson for today. Just know how to find equations of other lines that are perpendicular to the given line, okay? So that's the lesson on perpendicular slopes. So what I want you to do is to please, is homework 104, okay? Which you're gonna find in Schoology or Scheduler. That is gonna be due to Thursday, April 30th, okay, 2020. All right, so again, thank you for watching and have a great day.